In this lecture, we will discuss Chapter 2, which talks about determinants of n by n matrices. In the first two sections, 2.1 and 2.2, we will try to determine the determinants of square matrices using the cofactor expansion and row reduction. So we recall from section 1.4 that for a given 2 by 2 matrix, say A with entries A, B, C, D, this matrix is invertible if and only if the number AD minus BC is not equal to 0. We said that this number AD minus BC is called the determinant of A, and we denote this by det A or by these vertical bars enclosing A, or we replace the square brackets of this matrix by vertical bars like this. So we extend this notion to other square matrices of any size, not just 2 by 2, but also 3 by 3, 4 by 4, and etc. Now, for a 1 by 1 matrix, we just denote it like this. So square bracket, and then we denote this A11 as the entry of that 1 by 1 matrix. The determinant, which we denote by det, and then this matrix is the value equal to A11. So the value of the entry is the determinant of this 1 by 1 matrix. If we use this notation, okay, then for the 2 by 2, for the 2 by 2 matrix with entries A11, A12, A21, A22, then the determinant of that 2 by 2 matrix is equal to the determinant of A11 times the determinant of A22 minus the determinant of A12 times the determinant of A21. So observe, if we are going to replace this as your A, B, C, D, okay, then this is simply A, this is D, minus you have here B, and then this is your C. So this still follows the formula that we know for 2 by 2 matrices. Now, if A is a square matrix, we define the minor entry of Aij, which we denote by Mij, and this is obtained by getting the determinant of the submatrix that remains after the ith row and the jth column are deleted from A. We also define the cofactor entry of Aij, and this is the number -1 raised to I plus j times capital Mij. And we denote this number by capital Cij. So notice the subscript Ij, okay, it's the ith row and the jth column. Okay, it is related to the exponent of -1 in here. Okay, so -1 raised to I plus j, and of course the subscript of capital C is the same as the subscript of capital M, the minor entry here. Okay, so to understand this better, let us consider this matrix A. So we have this matrix A and we want to find the minor and the cofactors of the matrix A. So let us start with M1, 1. Okay, so this is equal to, so it says the minor entry of A11, which we will denote by M11, is defined to be the determinant of the submatrix that remains after the first row and the first column are deleted from A. So this is your entry A11. So we delete the row containing that entry and the column containing that entry. So the submatrix that remains here is just this guy here. Okay, so here M11 is the determinant of the matrix 1, 2, negative 3, negative 1. And this is just a 2 by 2 matrix, so we can use the formula. We will have 1 times negative 1 minus 2 times negative 3. So this is equal to 5. Okay? Now, let us consider M1, 2. Okay? M1, 2. So this time, we will be looking at the entry 1, 2. So this is the entry 1, 2, first row, second column. And this is the row that we are going to delete. This is the column that we are going to delete. And therefore, M12 is the determinant of the matrix 0, 2, 5, and negative 1. So if we calculate this is just 0, okay, minus 5 times 2. So this is equal to negative 10. M13. So this time we are going to look at entry A13 on the first column and or sorry, on the first row and third column. So this is the first row and the third column. So we delete this column, we delete this row. So first row and third column are deleted. So M13, it's the matrix or it's the determinant of the matrix 0, 1, 5, and negative 3. So if we calculate this is simply 0 minus 5. So this is equal to negative 5. So here are the minor of the entries in the first row of the matrix A. Let us calculate the cofactors before we calculate everything else. So we want now C11. C11, and according to the definition, it's equal to negative 1 raised to 1 plus 1 times M11. Now, 1 plus 1 is equal to 2, so negative 1 squared, that's positive 1, and M11 is equal to 5. So C11 is also equal to 5. For C12, okay, we will have negative 1 raised to 1 plus 2 M12, okay? But negative 1 raised to 1 plus 2, this is also negative 1. So we will get negative 1 times M12, it's negative 10. So this is equal to positive 10. For C13, this is equal to negative 1 raised to 1 plus 3 M13. And negative 1 raised to 1 plus 3, this is positive 1. M13 it's equal to negative 5. So C13 is equal to negative 5. Okay. Now let us calculate for the minor and cofactors on the second row entries. Okay. So here we are now looking at, say, we want to find M21. Okay, so second row, first column. This is second row, first column. So we delete the second row, we delete the first column. So this is equal to the determinant of the matrix 3, negative 1, negative 3, negative 1. So this is equal to, we have here 3 times negative 1. Let me write that as negative 3 minus 3 or negative 3 times negative 1, that's positive 3. So minus 3, this is equal to negative 6. M22. So second row, second column entry. So this is second row, second column. So we delete the second uh, row and the second column also. So this is equal to the determinant of the matrix 1, -1, 5, -1. So this is equal to, we have 1 times -1, this is -1, minus 5 times -1, that's -5. So this becomes 1 minus 1 plus 5, this is equal to 4. And M23, second row, first column, or second row, third column. So this is second row, third column. So this guy here, it's our second row, third column. Okay. And we want to delete this third column and the second row entry. Okay. So M23, it's the determinant of the matrix 1, 3, 5, -3. So this is equal to 1 times -3, that's -3, minus 5 times 3, that's 15. So this is equal to -18. For the cofactors, we have C11, oops, sorry, it's C21, okay? So C21, and for the C21, we have -1 raised to 2 plus 1 times M21. But 2 plus 1, it's 3. So -1 to the third power, it's still -1. And M21, it's -6. So we have negative of -6. This is equal to +6. C22, this is equal to -1 raised to 2 plus 2, M22. And we have 2 plus 2, that's 4. -1 to the 4, that's +1. M22, it's simply +4. And then C23, we have -1 raised to 2 plus 3, M23. And -1 raised to 2 plus 3, that's -1 also. So we have negative of M23, which is -18. So this is equal to +18. Okay. Now, let us look at the third entries, or the third row entries. So we have M31. M31, okay? So this is the 31 entry, okay? Third row, first column, so we delete this and this. We only have the determinant of 3 times 3, -1, 1, and 2, okay? So this is equal to 3 times 2, that's 6, minus 1 times 1, or 1 times -1, that's -1. So this is equal to 7. M32. For the M32, this is the 32 entry, okay? This is the 32 entry, third row, second column. So we delete this and we delete this. We will only have the determinant of 1, -1, 0, 2, and the determinant is just equal to 2. And for the M33, okay, for the M33, we have the following. So this is the 33 entry, third row deleted, third column also deleted. So we only have the determinant of 1, 3, 0, 1. Okay, 1, 3, 0, 1. And this is equal to 1. For the cofactors, we have C31. This is equal to negative 1 raised to 3 plus 1. M31. 3 plus 1, it's 4. So negative 1 to the 4, it's positive 1. And M31 is equal to 7. So this is just 7. C32, this is negative 1 raised to 3 plus 2. M32. Negative 1 raised to 3 plus 2, this is negative 1. And then M32, it's 2. So this is just negative 2. And finally, M33. M33, this is equal to negative 1 raised to 3 plus 3. M33. Okay, sorry, we are computing C33 in here. So we have C33 in here, and C33, it's negative 1 raised to 3 plus 3 times M33. 3 plus 3, it's 6. Negative 1 to the 6, that's positive 1. M33 is equal to 1. So this is equal to 1. Okay? So if you notice here, if we try to go back, the value of C, okay, the value of the cofactors is either equal to the value of the minor or the negative of the minor. Okay, just like this C31, the value is equal to M31, but C32, the value is equal to the negative M32. Okay? And what is this? So, yep, I have this uh, blank examples here. So a minor Mij and its corresponding cofactor Cij are either the same or negatives of each other, just like what I mentioned earlier. For the cofactor, it follows this checkerboard pattern. So we have the plus minus, plus minus, plus minus also along the columns, plus minus, etc. The pluses is just the factor negative 1 or positive 1 being multiplied to the minor. And the minuses is the factor negative 1 being multiplied to the minors. Okay, so pluses and minuses, these are just the multipliers. Okay, so now let us go back to this matrix, 2 by 2 matrix. Okay, so the 2 by 2 matrix in here, let me expand this 2 by 2 matrix. So we have A11, A12, okay, A21, and A22. So this is the 2 by 2 matrix. Okay, so we want to get C11, C21, C12, and C22. Okay, and of course, that will be easy to see. Okay, so here, let us look at this matrix. C11, it's negative 1 equals negative 1 raised to 1 plus 1 times the minor M11. Okay, but if you look at this matrix here, okay, M11, so for the entry M11 or entry A11, we delete this guy here. Okay, we delete this row and column, and we delete this row. And M11 is just the determinant of A22. And therefore, this is simply A22. Okay, and notice, negative 1 raised to 1 plus 1, that's positive 1. That's why we only have here A22. Similarly, for C21, you have negative 1 raised to 2 plus 1 M21. So second row and first column. So this time we have this guy here, second row, first column. So we delete the first column, we delete the second row, and we are left with A21 or A12. So this is equal to A12. Okay, I think I have erased this. So this is A22. Okay, but in here we have exponent. 2 plus 1. So negative 1 raised to 2 plus 1, that's also negative 1. So we have a negative in here. Okay? If we compute, okay, if we compute all the rest, the other two guys here, okay, we will be able to get the other values like for C12. For C12, this is the entry, okay, this is the entry here, 1, 2, we delete this column, we delete this row, and we will have A21. But this one is equal to negative 1 raised to 1 plus 2 M12, and therefore we will get negative A21. For C22, we will have negative 1 raised to 2 plus 2 M22. Okay, so for this guy, we delete this here. We get this entry. We delete this column. We delete this row. And we will only get A11. Okay, so notice, recall that the determinant of A using our formula, this is equal to A11, A22 minus A12, A21. So this is our standard formula. Now we want to write the determinant in terms of the cofactors. Okay? So to be more precise, I want to write the determinant of A using the cofactors on the first row entries, meaning the first subscript are 1, 1 or R1. Okay, the first subscript is 1, I mean, and we retain the other numbers that we will see here. So what I'm saying is, for example, in this formula, C11 is equal to A22. So this A22 here will replace that C11. And in here we have C12, it is equal to negative A21. So in this formula here, this is negative, and then we have here A21 here. So negative A21, we will replace that by C12. Okay? So C12. Okay? And for the other guys, for the other entries here, we'll just retain that. So we will have A11, and then in here plus A12. So notice this is plus now because the negative was transferred to A21 to write it as C12. So notice the subscript for A11, it is attached to the subscript, it is attached to the C with subscript 11 also. The A12, okay, subscript is 12. A12 is attached to the C with subscript 12 also. And we can do this in other ways, okay? We can do this using other ways. So for example, we want, we want to retain the subscript, the second subscript 2, meaning the second column, okay? So we have C12 and C22. So if we try to write this now, determinant, C12, again, it's negative A21. So we have it here already. So this becomes a C12. And then, of course, attached to it is A12. Whereas the value C22, it's A11. And this is our A11. So we will replace that A11 with C22. Okay. Okay. So A11 is C22. And this guy here, let me just write it. This guy here, this becomes C22. So the one retained is A22 in here. So you have A22. So again, just like before, C12, it's attached to A12. In here, we have C22, it's attached to A22. Okay? And we can do this. We can do this to, say, first column. So we will retain um, we will retain A11 and C1. Sorry, we will retain C11 and C21. So we are retaining the first column for the cofactors, and the other guys will be replaced. Okay? The other guys will be replaced. So C11 will be A22, C21 will be negative A12. Okay? So C11, it's this A22 here. And we said that C11 is attached to A11. So you have A11. And then we still have the plus in here. Why plus? Because C21 in here, it's negative A12. This is the negative. This is 1, 2. Okay, so negative A12 will be replaced by C21. Okay, so this guy here will be replaced by C21 and A21 will be retained. So you have A21. So notice C21 now is attached to A21, etc. Okay, and notice that all of these values are the same. They all give the determinant of A for the 2 by 2 matrix. Okay, so we extend this notion to n by n matrices. And in order to find the determinant of an n by n matrices, okay, we can simply follow the rules that we can deduce from this guy here. Okay, so if A is an n by n matrix, then regardless of which row or column of A is chosen, the number obtained by multiplying the entries in that row or column by the corresponding cofactors and adding the resulting product is always the same. So for example, in here, we choose first column. So the entry A11 is multiplied to the cofactor corresponding to A11 plus the entry A21 is multiplied to the cofactor corresponding to A21, which is C21 in here. So you have A11 C11 plus A21 C21. For example, now we use second column. Okay, so the entry A12 is multiplied to the cofactor corresponding to A12, which is C12 in here, plus the entry A22 is multiplied to the corresponding cofactor, which is C22 here. So you have here A22 C22 plus A12 C12, and etc. We can use also the first row. The entry A11 is multiplied to the cofactor C11 plus the entry A12 is multiplied to the cofactor C12. Okay? But the theorem is saying that this number here is the same as this number here, it's the same as this number here. Okay? So the resulting product and sum is always the same. Okay? So that resulting number is called the determinant of A. So if A is an n by n matrix, and then the number obtained by multiplying the entries in any row or column of A by the corresponding cofactors and adding the resulting products is called the determinant of A. The sum themselves are called cofactor expansions of A. So for example, in here, we want the cofactor expansion along the jth column. So meaning we are using the jth column of the matrix A. We are retaining the second subscript as j, and we run all the first subscript all throughout the rows. So here, the determinant of A is equal to A1j C1j plus A2j, C2j plus until ANJ, CNJ. So we are retaining the second subscript, the jth column. Or we have the cofactor expansion along the ith row. So here we are retaining the first subscript, okay, as I, because we are looking at the ith row. So here we have AI1 times CI1 plus AI2 plus CI2 plus until we have AIN CIN. Okay? So to understand this more, we will look at some of the example. For example, this guy here. We want to find the determinant of this matrix 1, 3, negative 1, 0, 1, 2, 5, negative 3, negative 1. So for example, let us use the first column in here. Let us use the first column in here. Okay? So it says that the determinant of A, this is equal to first column. So we have A11, C11 plus A21, C21 plus A31, C31. Okay? So now let us calculate this number here. A11, we have 1 times C11. So if we are going to look at C11, this will be negative 1 raised to 1 plus 1 times the determinant. Okay, determinant. So this is your A11 entry. Okay, we we remove this row here. We remove this column here. Okay, so we will be left with 1, 2, negative 3, negative 1. Okay, so the determinant of 1, 2, negative 3, negative 1. We have here 1, 2, negative 3, negative 1 plus A21, it's 0 here. So 0. And then whatever your C21 is, this is just 0. Okay? Plus A31. Okay? So this is your A31 here. Okay? So it's positive 5. So A31, this will be 5. And C31, it's negative 1 raised to 3 plus 1 times the determinant. So this is your A31. We remove this row. We remove this column. We'll just have this matrix here. Okay? So determinant of 3, negative 1, 1, 2. Okay? And we calculate this. We will have what? 1 times negative 1 raised to 1 plus 1. So this is just positive 1. So in here, we will get 1 times negative 1. That's negative 1 minus negative 3 plus, times 2. That's negative 6. Okay? Plus, of course, this guy here is 0. And then you have 5. Negative 1 raised to 3 plus 1. Okay? And 3 plus 1 is 4. So negative 1 raised to 4. This is positive 1. But this guy here, we will have 3 times 2. We have 6 minus 1 times negative 1. We have negative 1. Okay? So if we calculate this is equal to 5 plus, so that's negative 1 plus 5, plus 6. So it's positive 5. Here you have 6 minus negative 1, 7 times 5. So you have plus 35. This is equal to 40. Okay? Now, to verify the theorem, suppose let us use another column or row. In particular, let us just use this row here, row 3. Okay? Let us use this row 3. So the determinant of A can also be calculated using that expansion. Okay, determinant of A, this is equal to. So row 3, this guy here, so you will have 5 times negative 1 raised to, sorry, let me write first the expansion. So using row 3, we have A 31 C 31 plus A 32 C 32 plus A 33 C 33. So looking at the row 3. A31 C31 we already have in here. So let us just write that A31 C31 there. So we have 5 times negative 1 raised to 3 plus 1, determinant 3, 2, negative 1, 1. Okay? Plus A32, we have is negative 3, negative 3. Then the C32, it's negative 1 raised to 3 plus 2. Okay? Determinant. So 3, 2, and 3. This is your 3, 2, and 3. We remove this, we remove this. So we are left with the submatrix 1, 0, negative 1, positive 2. Okay? So we have 1, 0 here. So we have 1, oops, 1, 0, negative 1, positive 2. And then we have the A33 entry. A33, so this is your A33 entry. We have negative 1 times negative 1 raised to 3 plus 3. Okay, 3 plus 3. And then the determinant. So this entry here, we remove this column, we remove this row. We will only have 1, 3, 0, 1 in here. So if we calculate this, we have already calculated this guy here. It was this guy here. So we will have 5 times 6 minus negative 1 plus. We have here negative 3 times negative 1 raised to 3 plus 2. That's another negative number. Yeah, that's another negative number. So we have positive 3 times the determinant 1 times 2. So you have 2 here and then minus 0 here. Okay? Then plus. Here you have negative 1 times negative 1 raised to 3 plus 3. 3 plus 3 is 6. Negative 1 raised to 6. That's positive 1. So you have minus 1 here. So minus 1 times 1 times 1 minus 0 times 3. Okay? So if you simplify this, you will get 35 plus 6 minus 1. And this is equal to 40. Okay? So again, the same value as this. Okay? So choose whatever number you want. Choose whatever column or whatever row you want to determine the determinant of the matrix. You should get the same answer. Now, as a tip, try to choose a row or a column that contains many zero. Just like this guy here, this column, okay, we are looking at this column. And on this entry here, we have 0. It's now multiplied to whatever number C21 is. It's still 0. So in that sense, you are reducing the number of computations. Okay? Let us look at this. So we want to find all the minors and cofactors of A, and we want to find the determinant of A. So I'll leave to you the first part. Try to find the minors and cofactors of A. What we're going to do, what I will show is to find the determinant of A. Okay? So determinant of A. For the determinant of A, we can choose any row or column, and I'm gonna choose the third row here because it contains 0. You can also use first column because this contains 0, or the second column which has 0 also. Or you can use second row because it has 0 also. So I'm going to use the third row. The third row, it's A33 C, sorry, A31, A31 C31 plus A32, okay? C32 plus A33 C33. Okay? So we are looking at this guy here. Okay? So A31, that's 4. And then multiplied to C31, it's negative 1 raised to 3 plus 1. But we are going to delete the third row first column. So this is multiplied to the determinant of 1, 6 to negative 3. Okay, so we have deleted this first column and then the third row. Okay, for the next A32, that's again 0. This A32, this is the A32 entry, that's 0. And whatever your C32 is, it doesn't matter because you are multiplying 0. Plus A33, we have 2. Okay, we have 2 times negative 1 raised to 3 plus 3 times the determinant. So this is the entry. We remove this column here. We also remove this row here. We'll just have the matrix 4, 1, 0, 2. So if we calculate this, we will have, so 4 times negative 1 raised to 3 plus 1, that's positive 1. So this is just 4 times. We have here 1 times negative 3, that's negative 3, minus 2 times 6, that's 12. Okay? And then in here, you have negative 1 raised to 6. So positive 1. So we'll just have plus 2 times. And then you have 4 times 2, that's 8. Then 0 times 1, that's 0. So if we simplify this, we have negative 3 minus 12. That's negative 15 times 4, that's 60. Or negative 60 plus 8 times 2, that's 16. And this is equal to negative 44. So this is the determinant of this matrix. And as I have said, even if you use the first column or the second column or the second row or any other column or row for the matrix A, you should be able to get this determinant value. Okay? Another example here, we have to find the determinant of this 4 by 4 matrix. And let us follow the tip that I gave. Let us use the column or the row with plenty of zeros. So in this, we use this second column. So we use this second column, okay? So the determinant, so let me label this as your A. So determinant of A, this is equal to, so we have this 0, 831, okay, or A21, and then this is your A22, okay? But in any case, this is just 1 times negative 1 raised to, this is the 2 entry, so you have 2 plus 2, okay? Times the determinant, okay? Determinant, and then let us look at this guy here. We remove this column or row, we remove this column. So what's left is the matrix 1, negative 1, 3, 5, negative 1, negative 1, negative 2, 2, 1. Okay? So here you have 1 times negative 1 raised to 2 plus 2. And negative 1 raised to 2 plus 2 is positive 1. So basically, we are just computing the determinant of this matrix here, which is a 3 by 3 matrix. And we don't have the formula for 3 by 3 matrix yet, or the determinant of 3 by 3 matrix yet. So let us use this cofactor expansion. We can use any column, as I have said, or any row. So in this case, there are no zeros anymore. So let us just use first row in here. And using that, we will have 1 times the 1, 1 entry. That's the 1, 1 entry times negative 1 raised to 1 plus 1 determinant. So we remove this row, we remove this column. We will have negative 1, negative 1, 2, 1 plus. Okay, plus. Let us take this guy here. So negative 1 times negative 1. This is now the 1, 2 entry. So 1 plus 2. Determinant. Okay, this is the 1, 2 entry. Determinant. So we remove this column, we remove this row. We will have 5, negative 1, negative 2, positive 1. And then the last guy here, we have 3. So plus 3 times negative 1 raised to, this is the 1, 3 entry. So 1, 3. Okay. Determinant. We remove this column, we remove this row, we'll just have 5, negative 1, negative 2, 2. So if we calculate this now, we will have, this is 1 times negative 1 raised to 2, so positive 1. So this guy here will just have negative 1 minus 2 times negative 1, that's negative 2, okay, plus. Here you have negative 1 times negative 1 raised to 1 plus 2. This is positive 1 altogether here. So times, you have 5 times 1, that's 5, minus negative 2 times negative 1, that's positive 2. Then plus 3 times negative 1 raised to 1 plus 3, that's positive 1 again, so 3. Okay, and in here you have 5 times 2, that's 10, minus negative 2 times negative 1, that's positive 2. Okay, so now we are left with simplifying this, negative 1 plus 2, that's positive 1, plus 5 minus 2, that's 3, plus 10 minus 2, that's 8, plus times 3, you have 24. Yeah, and therefore this is equal to 28. Okay, so provided that I have the correct arithmetic here, we have 28. Okay, okay, next example. Here we have a triangular matrix. Okay, so we want to find the determinant of this triangular matrix. Let me label this as matrix A. So using our tip, this column here has plenty of 0. So let us use that first column in here. Okay, so the determinant of A, this is equal to, we have the A11. It's the entry negative 1 raised to 1 plus 1. Determinant of the remaining submatrix, which is this guy. Okay, so we delete this, we delete this, okay? So the remaining it's A2, 2, A2, 3, A2, 4, then 0, A3, 3, A3, 4, 0, 0, A4, 4. Again, we don't have the formula for this 3 by 3 matrix yet. So we look at this determinant and find it using cofactor expansion. And this row or this column here has plenty of zeros. So we take these zeros here. So notice we did not write anything else here because you have just 0, 0, and 0. So 0 times whatever the cofactors, they're just 0. So in here now, we have A1, 1, because this guy here, it's negative 1 raised to 1 plus 1, it's positive 1. But this, we have the entry A22, A22, and then negative 1. Take note that in this 3 by 3 matrix, A22 is the 1, 1 entry. So the exponent will be 1, 1, 1 plus 1. And then the remaining, so we delete this row, we delete this column. So the remaining submatrix will be 3, 3, A3, 4 here, 0, and A4, 4. And now we just have a 2 by 2 matrix here, so we can calculate easily the determinant. But we will see that the determinant of the matrix A here, this is equal to A11 times A22, negative 1 raised to 1 plus 1, that's positive 1. 2 by 2 matrix, we have A33, A34, minus, oh sorry, A44, minus 0 times A34. Okay? And therefore, the determinant of that triangular matrix is simply A11, A22, A33, and A44. So the product of these four guys here. So in fact, this is a formula. The determinant of any triangular matrix, it is equal to the product of the diagonal entries. Okay, so you just need to multiply the diagonal entries of the triangular matrix and you have the determinant. Okay, now we have determinants of 2 by 2 and 3 by 3 matrices. So we have a formula for the determinant of 2 by 2 matrices. So in here we will have another formula, this time for the determinant of 3 by 3 matrices. So here we have the following. The 2 by 2 matrices, we have arrow down here and then arrow going down here. Okay. Then here you have arrows going down to the right and arrows going down to the left. So what do they represent? Okay. So what you're going to do is on the same arrow, you multiply them. Okay. You multiply the entries. So A11 times A22. Here you have A12 times A21. Okay. And if your arrow is going down to the right, you multiply, you just take the product or multiply it by positive 1. Okay. And when your arrow is going down to the left, you multiply the product here by negative 1. Okay. And then you add all of them. Okay. Same is true um, with this 3 by 3 matrices. Okay. So here you will have plus here, plus here, plus here, while for the other guys, you have minus, minus, minus here. Okay? And for me, personally, what I do instead of going down to the left, I have going up to the right, going up to the right, okay? Which you will see most of the time in my computation, okay? So what did I describe? On the same arrow, multiply the entries, arrows going down from left to right, add them, and arrows going down from right to left, subtract them, okay? So for example, here, find the determinant of this matrix using the method described in here. So this is a 3 by 3 matrix, this is a 3 by 3 matrix. So what do? We augment first the first two columns of the 3 by 3 matrix, okay? So let us write that. You have here, let me adjust this. I will need some space there. So you have 4, 1, 6, 0, 2, negative 3, and then 4, 0, 2, 4, 0, 2, okay? And then we augment the first two columns. So you will have here 4, 0, 4, okay? And then 1, 2, 0, okay? So what do? This is your arrows going from left to right, okay? So we multiply them, okay? We multiply them. And when we multiply, we have 4 times 2 times 2, that's 16. 1 times negative 3 times 4, that's negative 12. We have 6 times 0, that's just 0. Now, for arrows going down from right to left, what I'm going to do is going up from left to right. So this is this guy here, okay? This is also this guy here. And finally, you have this guy here. So for the green ones, we have 4 times 2 times 6. So we have 4 times 2, that's 8, times 6, that's 48. Okay, and then you have 0 times whatever, so that's just 0. Then here 2 times 0 times 1, that's again 0. So what now? The determinant, okay, the determinant of the matrix. So if I name this as matrix A, determinant of A, so we will add all of these blues here. 16 minus 12 plus 0, minus because there's negative in here, okay? And then we will subtract the greens. So minus 48 plus 0 plus 0 plus 0 plus 0. And in here, what do we get? We will have 16 minus 12, that's 4 minus 48. And this is equal to negative 44. So this is the same value that we obtained earlier, okay? This is the same value that we obtained earlier. Next example here. So this is the same matrix as before on the previous example. So we should expect the same value as in that one. But this time we use the method described above. So we have 1, 3, negative 1, 0, 1, 2, 5, negative 3, negative 1. And then we augment first two columns, 1, 0, 5, 3, 1, negative 3. Okay? And then here we have the going downs from left to right. Okay? Okay? So we have negative 1 for this first blue here, and then we have 30. This is 3 times 2 times 5, that's 30, and then this is 0. And for the green ones, we have the going up in here. Okay, going up in here, and going up in here. So for the first 5 times 1 times negative 1, that's negative 5. Then you have negative 3 times 2 times 1, that's negative 6. And then we have 0 here. So if I label this as the matrix B, okay, we have the determinant of B. Determinant of B, this is equal to, so for the blue ones we add, so negative 1 plus 30 plus 0, let me just write that plus 0, minus, for the green ones there, we subtract, negative 5 minus 6, and then here. So what do we get? Here we will have 29 minus, here we will have negative 11. And 29 plus 11, this is equal to 40. So this is the same number that we obtained earlier. Okay? Okay, so now let us go to that second section 2.2, but to begin, let us start with these theorems. So if A is an n by n triangular matrix, then the determinant of A is the product of the entries on the main diagonal of the matrix. So we have seen the example earlier. But you can prove this for the general n by n triangular matrix. So same solution as in the example we had. Now, let A be a square matrix. If A has a row of zeros or a column of zeros, then the determinant of A equals 0. So this one is easy to prove because if you have a row of 0, then just get the cofactor expansion along that row with everything is 0. So the determinant will be equal to 0. Now, let A be a square matrix. Then the determinant of A equals the determinant of A transpose. And again, this is quite trivial because, for example, if you have the matrix A, you find the determinant of matrix A along the ith row. Okay? Now, get the A transpose. The ith row becomes the ith column. Okay? So, try to find the determinant of A transpose by using cofactor expansion on the ith column. And you will still get the same value. So, the determinants of A is equal to the determinant of A transpose. Let A be an n by n square matrix. Now, if B is the matrix that results when a single row or a single column of A is multiplied by scalar k, then the determinant of B equals k times the determinant of A. Okay, so in this, it seems that since the matrix B is almost the same as the matrix A except for a single row or a single column, okay, which is multiplied actually by k of that single row or single column of A. Okay, so what do we do here? We can just factor out that k, and the determinant of A multiplied to that factor k, that will be the determinant of B. Okay, if B is the matrix that results when two rows or two columns of A are interchanged, then the determinant of B equals the negative determinant of A. So if you interchange two rows or you interchange two columns, you will put out a negative outside. Okay? Now, if B is the matrix that results when a multiple of one row of A is added to another row of A, or when a multiple of one column of A is added to another column of A, then the determinant of B is equal to the determinant of A. So meaning the determinant does not change. Okay? But what are these? These statements here, the first, the assumption here are just your elementary row operations. So, or elementary column operations. Okay? So, in the first guy here, okay, you actually have K row I. Okay? You change the row I to K row I. Okay? For the second statement here, your row I interchange with row J. Okay? On this guy here, the last one here, you have row I plus K row J. So this replaces row I. So these are all elementary row operations. But what happens to the determinant? Again, for the first row operation in here, the determinant is multiplied by K. Okay, the determinant of the original matrix is multiplied by K. Here, the determinant of the original matrix is negated. And in here, the determinant is the same as the determinant of the original. Okay, so we will see an example for this to show how things go on. Okay, if we now consider an elementary matrix E, okay, what do we get? So if E results from multiplying a row of In by a non-zero number K, then the determinant of E equals K. Since you started with In, you multiply K to a single row, okay, you will take out that K. Then multiply to the determinant of In, but the determinant of the identity matrix is simply 1. Okay? If E results from interchanging two rows of In, then the determinant of E equals -1. Because you interchange two rows, you will put out a negative. But determinant of In, it's 1. So you just have -1. If E results from adding a multiple of one row of In to another, then the determinant is the same as the determinant of In, which is equal to 1. So this theorem here is the same as the previous theorem, but we have a good matrix here, elementary matrix. Okay? So, for example, in here, find the determinant of this matrix using row reduction. So we want to find the determinant of this matrix using row reduction, meaning the methods that we just had. So we want to find the determinant of the matrix 4, 1, 6, 0, 2, -3, okay, 4, 0, 2. Now, our goal here is uh, to do a row reduction to reduce this matrix such that the matrix is triangular matrix, particularly upper triangular matrix. Why? Because as in before, we have a formula for the determinant of the upper triangular matrix, just the product of those diagonal entries. So we will try to reduce this into a triangular matrix. So how do we do this? First, what we can do, we make this 0. And to make that 0, so the row reduction that we're going to use is that we have row 3 minus row 1. Okay? This is the third row operation that we discussed. So what will happen to the determinant? It's the same. Okay? It's the same. So we will have 4, 1, 6, 0, 2, -3. And then 4 minus 4, that's 0. 0 minus 1, that's negative 1. 2 minus 6, that's negative 4. Okay? Okay? Now, next, we want to make this 0. Okay? We want to make this guy here 0. Okay? So what we can do is to replace row 3 by row 3 plus 1 half, 1 half row 2. Okay? Replace row 3 by row 3 plus 1 half row 2. Okay? So let me use green ink there. So row 3 plus 1 half row 2. Okay? And again, this is the third row operation, so the determinant remains the same. So we copy first row 4, 1, 6. We copy second row 0, 2, negative 3. And for the third row, we divide everything. We divide row 2 by 1 half, by 2, sorry. Then we add it to row 3. So negative 1 plus 2 times 1 half, that's 1. So this becomes 0. Here you have 0 plus 0. And in here you have minus 4 plus 3 halves or negative 3 halves. So you have minus 4 minus 3 halves. Okay? And notice nothing has changed in here, but we were able to reduce the matrix into a triangular matrix. So what we can do now is to multiply all of these entries here, diagonal entries here. So you will have 4 times 2. And then in here you have what? Negative 11 halves. Negative 11 halves. And you will get negative 44, which is the same value that we obtained earlier. Okay? Okay? So, notice determinants did not change. Okay? Determinants did not change in here because if we look at the things in this slide, we only use this item 3. Okay? So determinants did not change. But if we interchange two rows, okay, interchange two rows, we will have to put out a negative. For example, instead, if in here, okay, if in this guy here, from here, we interchange, okay, suppose we interchange row 2 and row 3, we will now have negative determinant of 4, 1, 6, 0, negative 1, negative 4, 0, 2, negative 3. Okay? And then we can make this 0. Okay? If we make that 0, and to make that 0, we'll just have row 3 plus 2, row 2. But we will not put, the determinant will change, but the negative is still there because of this negative here. But we will have now determinant of, we have 4, 1, 6, 0, negative 1, negative 4. And in here you have 2 plus or minus 2. That's 0. And minus 3, minus 8, that's minus 11. So still you will get negative of 4 times negative 1 times negative 11. And this is equal to negative 44. Okay? So whatever method you use, however you do the reduction, you should get the same value. But just make sure that you put out the proper negative if you interchange rows, or the column or a row was multiplied by some constant. You have to put out that one, the scalar multiplier. Okay. Now, if A is a square matrix with two proportional rows or two proportional columns, then the determinant of A equals 0. So how do you do this? Well, since they are proportional, okay, you can just, one of the proportional can be made to 0 by subtracting, okay? Subtracting that row from the scalar multiple of the other row. So you can see this one. You'll be able to see this guy here. So just one more example, okay? So in here, you have this matrix A. You can use row reduction, or you can use uh, column cofactor expansion. I think cofactor expansion is very good in here, because in this guy here, if you use this column here, okay, this has plenty of zeros. Yeah, maybe we can use that column expansion, cofactor expansion along the second column. So let us try. Determinant of A, this is equal to. So we'll be looking at the second column, okay? And the second column, we will have what? -1, okay? -1 times -1. This is a 2, 2, or 1, 2, and 3. So you have 1 plus 2. And then the determinant, if we look at this guy here, we will delete this column here. We will delete this row here. So we will get 0, 2, and then -3, and then 5, 10, -11, and then 4 to 1. 4 to 1. Okay? So notice this is a 3 by 3 matrix now. We can combine our method in finding the determinant of a 3 by 3 matrix. Okay? So if we use that guy, let us put this aside here. 0, 2, -3. We have 5, 10, -11, and then 4 to 1, 4 to 1, okay? And then we augment first two columns. So you have 0, 5, 4, you have 2, 10, 2, okay? And then going down in here, you have this matrix here, this matrix here. Oh, sorry, this diagonal here, this diagonal here, and then this diagonal in here. So this is 0, 2 times -11 times 4, that's -88. And then -3 times 5 times 2, that's -30. Okay, -30. And for the going up, we have this guy here. We also have this guy here. And finally, this guy here. So 4 times 10 times -3, that's -120. -120. Then we have 0 in here. Let me just write that. And then here, 1 times 5 times 2, that's 10. Okay? So with this, we will have, so -1 times -1 raised to 1 plus 2. Okay, that's positive 1. So this is equal to minus 88 because you just have 0. So 0 minus 88 minus 30. Okay, minus quantity minus 120. Okay, plus 0 plus 10. Okay, and we have here we have minus 118. Okay, minus 118, and then here minus 110, so plus 110, plus 110. So this is equal to minus 8. So the determinant is equal to minus 8. Okay, so that's our last example for this lecture, and thank you for staying.